Morning, everyone. My name's Howard. My partner in crime, Kevin Larnon, spoke yesterday. I should actually confess that Kevin and I actually developed Z++ some years ago, along with some colleagues at Oxford. And I can't really say that we are responsible for the reasons why formal methods are actually not being used in its earnest today. But having said that, we did get funding for a number of years, 5 years, as it turns out, I think from around 1989 through to about 1994 for a European ESPRIT project, applying formal methods to safety critical applications. So formal methods actually do work in some respects. By and large, I would agree with Jan, probably 99% in agreement, 1%. I would disagree, and I'll tell you why I disagree to an extent. But I think that he's probably right on most of the things. And I think when you see what I'm going to talk about when I go through the presentation, you'll see why I'm agreeing with him 99%. But then I made the transition into finance. I run a boutique financial risk management company, also associated with King's College London, in the Department of Informatics. And my talk today is really trying to get us to think about how can we apply MDE to financial model validation. Financial model validation. In fact, what is model validation? What is financial model validation? So what is a model? A model is defined by different regulators around the world. So for example, the US Fed defines a model using this phrase here, basically says that it's any quantitative method that you can apply, typically mathematical or statistical, to transform inputs into outputs, if you like. You could probably say that, well, actually, that's any kind of model, is it? Not necessarily a financial model, but that's what they say. Also, model validation are a set of processes and activities which do all of these things here. So let's ponder on this a little. This would seem to me that model validation can cover lots of different types of models. So an Excel spreadsheet is a model, for example. If you look at this, something which, not a piece of paper with some mathematics on it is a model necessarily, but anything which is executable can be defined to be a model. Okay. So what are the key steps in model validation? As far as regulators are concerned, and financial regulators, and why do I talk about financial regulators? In the world of safety critical applications, generally speaking, if software systems fail, people die. But in the world of finance, if systems fail, we lose money. And that seems to be today a little bit more important than people dying. So as far as regulators are concerned, there are really 4 things that they're interested in looking at. One is evaluating the soundness of the underlying conceptual framework. What does that mean? Supposing that you wanted to price an option on a stock, not that anyone's interested in the stock market here, I take it. But if you were interested in an option on a stock, you might want to know what's the sort of process for the evolution of a stock, if you will. So Jan kind of alluded to this earlier, he spoke about stochastic processes. So if you can imagine that you have a stock and the stock moves in a certain way. So stock price is always positive, and the stock can evolve according to a certain stochastic process. And generally speaking, we assume a sort of geometric Brownian motion for the movement of the stock. Now, having said that, we would have to verify that the stock moves according to geometric Brownian motion. That's one of the things that we'd need to do. We'd also need to evaluate the soundness of the quality of the software. So assuming that we've produced a mathematical specification and we've refined that specification into code, we have to ensure that the software quality is sound somehow. We also have to do an evaluation of the appropriateness of the use of the model. Well, this seems fairly straightforward, doesn't it? And also an evaluation of the reasonableness and the accuracy of the model outputs. Now, at this point, can you see any difference between validating, let's say, a model for, I don't know, hotel room occupancy, over this kind of model for, let's say, valuing a derivative like a call option? Can you see any differences at all? At this point, there should be none. However, there are consequences to financial institutions not adhering to these particular steps, namely that the regulators can actually suggest more regulations, the regulators can suggest that you can't use a particular model, let's say for pricing a derivative or for what they call risk capital or regulatory capital, if you like. And also they can impose fines. So there are consequences for not doing things correctly. So the main focus of this research work is to try and see, in essence, what would you require to have in a modeling language that would allow you to be able to, first of all, specify the properties that you want, let's say of derivatives, and then ultimately to be able to refine these into code. So what are the things that you want to do? A bit of a typo there, just two. Actually, there's two typos. Should be step one, not step two. Step one is really proving the conceptual completeness of the model. Step two is essentially going into code. For those that are not familiar with derivatives in finance, CIR is just the initials of some guys from the 70s who created a model. CRR, Cox, Frost, Rubinstein. It's a binomial model. If you're familiar with binomial trees, then this is a sort of discrete time process that you can use in order to evaluate the value of an option. And you will see here that if I had validated my own work, then I'd be able to spell binomial correctly, but I haven't. Okay, so one of the things that we want to do is to be able to specify some desirable characteristics of a MDE, and also we want to be able to focus on specification and proof. So imagine that we have this binomial model, and typically within finance, we want to validate a model against another model. So somebody who develops a model, like let's say if you're familiar with the Black-Scholes model, somebody who develops that model, somebody else may come along and say, well, I want to validate that model. But the validation of the Black-Scholes model will be with respect to another model. So some independent person will come along and say, here's another model that should somehow produce similar results to this model here. And so what they'll do is initially start off by looking at congruence between these models. In other words, a proof of equivalence between the two models. So we have to state what are some of the assumptions. Well, there are no arbitrage opportunities. Essentially, if I have an option and I can somehow replicate the payoff of the option in terms of having cash and a stock, then somehow by being long the stock, and if I bought an option, I should be able to take an individual amount of cash and an individual amount of stock and somehow replicate the payoff of that option. So arbitrage basically says I should be able to construct a portfolio in such a way that there are no arbitrage opportunities. We make some assumption about interest rates. This could be one of them. And we make the assumption quite often that investors are risk neutral. In other words, they're indifferent to investing in stocks which give a certain rate of return, as opposed to just investing, let's say, in a risk-free government security. So risk neutral, read into that government securities, if you will. Then we would define what is an option. So we would have some mathematical formula that we would use for expressing what the payoff would be. Now, think of a binomial model, if you will, as taking discrete steps, and every step that you take in order to work out where could the stock evolve to, the stock could either go up or go down in value with a certain probability. So in the model, these are all of the things that we would be writing. So as somebody who's developing a model would say, right, assuming that the stock starts off at a particular value, S0, at one step in the future, which could be 1 minute, could be 1 hour, could be 1 day, the stock price could go up or down with a probability P. What is that probability? Well, we're going to have to work that out. It could go up by an amount U, which is greater than 1, or it could go down by an amount D, which is less than 1. And then this arbitrage that I mentioned to you before, we have to avoid that. So we imply some constraints, which we have to prove. And we can construct a replicating portfolio. And I'm hoping what you're getting from this is that when you produce a model, there are lots of different equations that you have to ensure are correct. And you have to make some assumptions, which you also have to prove to be correct. So as we go through, for example, you needn't worry about what the consequences of H1 and H2 are. Suffice to say that there are lots of these different equations which you have to prove to be able to work out the value in today's money of a call option. So this is a very simple example where we've taken just one step into the future, one point in the future, could be 1 minute, could be 1 hour, and we have worked out what would be the value today, today's money, if we were to discount the payoff or the expected payoff of the option, let's say in 1 period's time. So the V0 refers to the today or the now value of that option. Just to give you a picture as to what a binomial tree looks like and how the stock could evolve, we initially start off with a value of, let's say S0, which is $100 or 100 pounds, and the stock could either go up or down. At every discrete point in time, there is a space within which the stock can either go up or down. And as we move forwards in time, then you'll see that effectively the combinations of stock prices go up and down increase across time. And so what we're trying to do is to model this and then to work backwards from the tree to time 0 to work out the value in current money. So we evolve the stock. We then look at the payoff, which we said is going to be a call option. There's a difference between the terminal value of the stock and say some strike. We work backwards. Each of these have a respective probability of occurring, and then we work out the expected discounted value in today's money. Okay. Now, the value of this, so get this expression, don't worry about it, but it's an expression which allows us to be able to work out the value in today's money using a binomial formula for the value of the option. So this would be a formula that the quantitative analyst who's developing this model would write down. Now, having said that, this model is a function of a number of discrete steps in time. So, for example, if I were to price an option which matured in 1 year using a tree, I may decide that I want to split the number of periods by, let's say, days in the year. So I could divide by, let's say, 250 or 252 business days in the year. So delta t here, the time n here would be 252. However, there are going to be certain paths through the tree where the option is 0 because there's no payoff, there's no value to you. So we then have to figure out what that is. So this is going to be a constraint in the actual implementation of the code for this. So we then have to do a refiguration of the call formula for the binomial option. We refigure what our probabilities of going up and down are. We then have to work out what are the Ds and what are the ups. In other words, what are the things that we need to multiply the stock by in every single point in space and time so that we can evolve the stock price. So we need to figure that out. As it turns out, this is actually quite complicated. You can figure out that this is a sort of quadratic equation in D. So we would have to solve for this quadratic value of D. And this is a accompanying paper that I'm writing to go through this proof. But basically, we would solve this and we get a value of D. We put that back into our formula for P. We then say no arbitrage means the numerator of this has to be positive, which is yet another constraint that we would have in the implementation. Some of the assumptions that we would make are, for example, using a Taylor series expansion for exponential in order to be able to simplify our expression so that we can derive this particular constraint here, namely that sigma is greater than the interest rate multiplied by the period of time over which we're evolving the stock. Also, we would want to be able to compare the Black-Scholes model, which we know to be correct, to this model. And so we use a stochastic process here, geometric Brownian motion, and we find out the limits of that. We work out the expectation to find the mean and the standard deviation, and we compare that to the mean and the standard deviation of a binomial process as n tends to infinity, because we know something about central limit theorem, which allows us to be able to say if we have a binomial distribution somehow as the number of combinations increases, then as n tends to infinity, we should get the same limiting distribution. as the normal distribution. Moreover, if it is that in the limit, the binomial is a normal distribution, what are the limits of the integration that we would have to do? So we would have to figure out what that is. So we have to do some transformation, subtract the mean and divide by the standard deviation. And in so doing, we are able to work out this very famous value for working out the value of whether the stock will be in or out of the money, as they call it. And so having done all of that, we form some conclusions. And what do we form? We say that we need to demonstrate conceptual soundness. It can only be done if it is that we have an MDE, which allows us to be able to express mathematical specifications and to be able to do non-trivial proofs. What's the second thing that we need to do? We need to be able to imply certain test cases or test conditions which can be incorporated within the actual software code itself. And some of these, when I went through the proof, may not have been obvious, but some of the proofs that I did would have to be translated into certain conditions that would be implemented within the software code. The MDE itself should formulate therefore, the derivation of proofs and also the auto-translation into code. Now, some of the things that we might want to do, for example, in an MDE, is to be able to do things like this: solve an expression for a number of parameters by making a substitution in yet another one. So these are things that we would want to do. And you saw an example of that when I was deriving the values for H1 and H2. I might want to prove, for example, that a certain condition is true on the basis of some predicates that I've set up. In this case, to be able to prove that epsilon is less than 1 or greater than or equal to 0, which is a necessary and sufficient condition in order to ensure that when we are summing in the binomial condition, that we are doing this with the minimum value of the integer greater than some number, such that the option is in the money. Other things that we might want to do is to be able to simplify expressions as well. So we'd want the ability to be able to simplify a mathematical expression. You may recall me saying that this could be reduced to a quadratic equation in D. I did everything manually and solved it, but it would have been nice to have had some tool support that would have enabled me to be able to solve for D and hence to be able to solve for the upward moves as well. And in a stylized MDE, we could do something like this: simplify this expression as a quadratic in D by expanding e to the y to first order, which is essentially a Taylor series expansion to first order, and also by ignoring terms in delta t, in other words, the time increments, which are greater than 1, because as n increases, delta t tends to 0. So that makes a lot of sense. And some of the conditions that you'd want to have in the implementation would actually derive from some of the proofs that you have just done. So, for example, we would want to implement this formula here for the complementary binomial formula for implementing the value of a call option by having a set of preconditions that we would want to do. You recall that looks very familiar to the condition that I had proved earlier to be necessary to avoid arbitrage, but also to have some code which is going to be asserted into the implementation, which are predicates, almost like a precondition as well, on, in this case, the variable a. So it's a constraint on a, which would also have to be embodied within the code itself. I think that takes me up to the end, right? Okay, so I appreciate that there are lots of things that I've spoken about that you perhaps never heard of before in terms of your experience in finance, but I really just wanted to concur with Jan in terms of some of the things that he had said, which is essentially that for the world of finance, we need to have tools which allow us to be able to model things, requirement specification, to be able to prove properties about the things that we have modeled, but also to be able to have the ability to be able to then auto-generate code, to have traceability between the specs, the design, and the code, because if we don't do that right, we're going to get fined. That's what we care about, is not to be fined. So essentially, there is some synergy between, I guess, the sort of high-tech world or the safety critical applications and the world of finance.
Thank you very much.
Okay.